Okay, let's go. Okay, I'm Teuntje, and together with Anton and Nihat, we'll talk about quantum computing, quantum algorithms, and quantum cryptography. So, first question is, why do we need quantum computers? Well, it has to do with quantum mechanics, and I'll give you a quick introduction into this. Let's first recall how we calculate the molecular orbitals of a hydrogen 2 molecule. So we have a hydrogen atom with the 1s orbital and another one in the with the 1s orbitals. We can construct the molecular orbitals by making a linear combination of these two orbitals, and then we get the bonding and anti-bonding orbitals, in which the two atomic orbitals are either in phase or out of phase. Well, for hydrogen, it's a very simple equation, but for something more complicated, like a water molecule, we have to consider more orbitals. For example, the oxygen atom has also p orbitals, and since it's oxygen, we need to include the 4 electrons in the p orbital, in the 2p orbital. And if we now look at which base sets we can use, this is the minimum base set, is the STO, and it only contains the filled atomic orbitals, like the s and the p orbital in this case. If we go to a slightly higher base set, then we can also include diffuse atomic orbitals. So the same orbitals, but then with different parameters for diffusion and everything. So we can have that the probability of encountering an electron drops off more slowly if we move away from the molecule. If we also want to model the dipoles on the hydrogen and the oxygen better, then we have to include an asterisk, which includes d orbitals on oxygen or p orbitals on hydrogen to polarize the electron cloud in one or two directions. And this is, these are the all different base sets, just to summarize, and these are the number of orbitals we get in these base sets. And if we want to model our water molecule the best, then we have these dipoles. So if we include more orbitals, it's better for our calculation. But if we include more orbitals, it's also more expensive for our calculation. And this was something which Richard Feynman encountered already in the 1970s, maybe, on his computer. He noticed that his computer wasn't up to speed, and he was thinking of maybe if he wanted to do calculations on molecules, he might need a quantum computer, because, well, the binary computers were really not up to speed yet. And he would need exponentially more memory and more bits to be able to crunch all these numbers. At the time, we were still quite familiar with analog computers, so computers that form an analogy with reality, like these gears form an analogy for the planets and Earth and the moon moving around us. But similar, we can build a quantum computer which is analogous to the quantum problem we try to solve. In this case, like the molecular orbitals of a molecule. So inside this Helium-Cool's thermostat, we have the quantum computer with our qubits, and these qubits are linear combinations of ones and zeros, both of them at the same time.
Hi, I'm Anton, and I'm going to talk about Shor's algorithm, one of the famous and privacy-breaking algorithms out there. I'll start by Rsa Cryptography, made by Ron Rivest, Ali Shimir, and Len Adelman, hence the abbreviation RSA. To encrypt their messages, they use multiple of two very large prime numbers, from which the prime factors of these numbers is really hard to find. It needs tremendous amount of time on a normal computer, on a classical computer, uh, until Shores came in and found a way to break this code really fast with the usage of quantum computers. Let's take two arbitrary numbers that doesn't have any common factor between themselves. In this case, a to the power of some specific p is equal to multiple n plus 1. In this context, a will be a randomly chosen number, and n will be the multiple of the prime numbers, the encoding. Of course, we can rearrange this formula in this form, which is really helpful because it tells us that a to the power of 1/2 p plus or minus 1, uh, even if they're not like the prime factor of n, it shares the prime factor. And by using a Euclidean algorithm, bam, we cracked the code. We found an algorithm. Well, not yet, because finding p is challenge on itself. That also takes a lot of time. Here comes the quantum part. What quantum computing allows us to do is to do this particular problem is that it allows us to leverage the superposition and do the computation in parallel. So we can have our guesses and the powers we raised in superposition, then do the computations. However, we cannot just measure the superposition then, because we will get the result of the measurement will be some arbitrary random element of the superpositions, which we don't want. But if we take the superposition and measure the amount more than the multiple, hence taking the remainder part, then we would randomly get another superposition of one of some of the possible answers. From this, thanks to a mathematical principle, we can take we know that a to the power of some arbitrary x, some multiple of n has some remainder, but if we take x plus the p that we are searching, it has the same remainder, no matter how many tries we do it. And in this equation at the bottom shows us, because AP is equal to multiple n plus 1, it will always have the same remainder here. And from that, we have all the values of superposition are p apart from each other. Therefore, we will find there will be frequency of 1 over p. That's a mistake. And and we can use the quantum Fourier transformation, which you can apply for the superposition that will cause the all-wrong frequencies to destructively interfere, leaving us only with the frequency 1 over p, which can be inverted back to p. Of course, it doesn't work always on the first try. As it says, it takes only 75%. But if you repeat enough times, you will eventually get it. And that's how we broke the code and that's how we break the encryption.
In our class, we learned about Heisenberg's uncertainty principle. And one of the things that this principle implies is that we cannot know certain pairs of properties simultaneously. One of these pairs is momentum and position. When we know all the information about momentum, we lose all the information about position. and vice versa. This also applies to vertical versus horizontal and diagonal versus other diagonal polarization. Imagine we have a randomly polarized photon, which passes through horizontal polarizing filter, and it becomes horizontally polarized photon. But this cannot pass through the vertical polarizing filter. It has a 0 chance of passing through. However, if we change the situation a little bit and place a 45-degree angled diagonal polarizing filter between the two other filters, the horizontally polarized photon can pass through this diagonal filter, because when it becomes horizontally polarized, it loses all of its information about its diagonal polarization. Therefore, it has 50% chance of passing through. And this diagonally polarized photon can pass through the vertical polarizing filter, because it lost all of its information about its horizontal polarization when it became diagonally polarized. So at the end, this total process had a 20% chance of passing through. Imagine Richard Feynman trying to send some message to Peter Shor. He creates an array of random bits and encodes this information with polarizations, with different orientations. Then Peter Shor makes a measurement to gain this information. He randomly measures the polarization of the photon in different orientations. And then Richard Feynman shares the information in which bits he shared and their orientations. Then they compare these ones, and in the cases that Peter Shor got the orientation correct, they use these ones to create a key. But there is something called the man-in-the-middle attack, which an attacker intercepts the message and learns the message before Peter Shor does. Well, in this case, the attacker also needs to measure the polarization of the photon. But the attacker in each scenario has a 50% chance of measuring in the correct orientation. If the attacker doesn't measure it in the correct orientation, it changes the photon. So at the end, when they exchange information, they won't know whether the message is intercepted or not, because in this last case, Feynman and Peter Shor measures the photon in the correct orientation. However, the attacker measures it in different orientation. Therefore, it changes the photon. So they would know whether the message is intercepted or not. And this is how quantum K distribution works.